Okay, so we're going to be covering algorithms today, and we are focused on selection sort first, then bubble, and then insertion. And then after we are done with these algorithms, we're going to talk about 2D arrays, and then assignment 1. Now, the way I'm going to cover these algorithms, I have some nice slides that the textbook author has gracefully provided, so I shared those with you. It also has animation. And I am particularly interested in just covering the way I learned these algorithms. So what I'll do is start with selection sort. So you have an array of elements. That are unsorted. So let's say something like this. Is that font size okay in the back for everybody? Yes. All right. Selection sort, the way the algorithm works is treat entire array as an unsorted array. Treat entire array as an unsorted array. Then find the smallest element and place it in the start of array. Okay, and then increment the sorted part of array by 1. And number 4, go to 2. If you have reached n minus 2 elements, then array is sorted, or then exit. Now you have to decide, obviously, if you are sorting in ascending order or descending. So I'm going to start with ascending order. And note takers, I'll post these online for you. You don't have to sit there and write. I would rather you spend your time thinking about each step, please. There's no need to sit and write. I mean, I'll take notes for you. I'll be online and So I'm going to create a variable called wall. Wall is this variable that creates a virtual wall in the array, and when the wall is 0, that means the entire array is unsorted. Like right now. So now I'm going to look in this entire array. I'm going to say which is the smallest element. Can you help me? Minus 96. So I'll create another variable called loc, and I will put 4 in it. Right? Because that's the location of my smallest value, minus 96. If you say 96, then of course it doesn't. So what I'm going to do is, since I found the location, I'm going to exchange these values. So I'm going to put minus 96 here. Then I'll have minus 4.
Really 4.
Oh, I'm exchanging wall and location, right?
Yeah.
Do you agree with me or do you disagree with me? You are okay with me so far? All right. Okay, so now wall is 1. I'm messing this up right now. I'll get it. There you go. Is that good enough? There you go. Never tried to draw graphs in Notepad. What is the location now?
1.
Location is minus 1? 1. Because there ain't any index value in that's minus 1 in the array, right? Do I need to do any exchange when wall is 1 and location is 1? No. So keep going, right? Keep going means what? Copy the array down as is. I don't need to change anything. And now wall is 2. And location is? Location is 4. You guys are getting good at this. So now I'll have minus 96, minus 4, 4, 144, 41, 240. You guys are very helpful. Now wall is 3. And location is? Still 4? It is still 4. So now what do I do? 41. And the wall is at 4. And location is? 4. Do I need to exchange? No. So if location is 5, then it must be the end of the array, right? So therefore the array is sorted. And this is how selection sort works, people. Get it? Yes, please.
I have a question. Why does it say if reach n minus 2 elements? Shouldn't be n minus 4?
N is the size of the array.
I don't know, but why is it minus 2?
Because index value starts at 0.
I was wondering if there's confusion.
Oh, you're right. Yeah, yeah.
You get lower every time you switch.
What does location mean? I mean, I kind of get it, but not really.
Location, okay. So what is wall?
Wall is like each and every pass. Every time you go through
Right. These are the kinds of walls I like to create. Right? Getting to a topic. So wall refers to number of sorted elements in the array. And location refers to the location of smallest element in the array, in the unsorted part of it. Now you see, if you want to become a really good coder, right? Here's what I'll request you to consider. You have this algorithm, write the code for it yourself. You have the book as backup. You can always go and look in the book, right? And because code is in the book, I'm never going to ask you to write it because your exam are open book and notes and you'll just go there and give it me. But my request is, you have this algorithm. Let's write the code. So, how will that work? Coding. I might have function that will return void and will be called selection sort, and I'll pass it a one-dimensional array. And this will call another function that will return an integer of the smallest element in the array. We'll pass the array, and since I already know the length, this function can return the smallest element. And then there will be another function that will be exchange values, that will take the one-dimensional array and it will take the two values that need to be exchanged. And these two will be subfunctions. Right? Do you guys see how that will work? So if you want to apply the knowledge of loops and decision making and passing by reference, you can just write this cute little program that will be selection sort. Selection sort is the easiest one to implement. Insertion sort is the hardest to implement. Okay? So this is your coverage on selection sort algorithm. My request is to now, we need to solve some problems. Because it won't make sense until you've solved a problem. So, okay, so here we have an array that we want to sort in ascending order. So wall, we're going to start off with 0. And I like things in the middle, so there we go. Location is 5. So keep going. What should I do? Copy the entire array down as is and exchange. Bring that guy here, and what should go there? Minus 20. Wall is 1 now, so that means this part of the array is sorted, right? And now location is 1. So if that is the case, there is no swapping, right? Maybe we have a little animation of our own. Wall is 2, location is 5. So we copy the whole thing down and swap those two. So I'll take 98 to the first value and bring 44 here. So, and now wall has become 3. Location is? Oh guys, something is wrong.
Wait, why didn't you bring negative 20? You gotta bring negative 20 over there. So it's...
Did I make a mistake?
Yes.
Undo. Okay, swap 2 and 5.
Yeah.
I was going to say, somebody will say something or not. And then 44 here? Ah. So now location is 5. Why is 5 the lucky one in this? So now we bring 44 and 96 and the rest of it down just like that. Thank you. And we bring this down. Location is, so no change. Wall is 5, location is? And now the array is sorted because we only have, because wall is 5. Okay? This is what you'll be expected to show for the output. And it's a different behavior with different algorithms. That's why we are going to cover these 3 algorithms with exercises in class, so you guys get really, really good with this, right? Our next example is asking the array to be sorted in descending order, which means the algorithm will change, and instead of looking for the smallest value, we're going to look for the highest. So wall is 0, and location is 0. That means what? No swapping. Location is 1. Wall is 1, location is? Oh man, this is a lazy algorithm now. Or wall is 2, location is? Isn't this already sorted?
Last 3 digits.
We still have to do all that work? But you have to go through it programmatically, right? When I ask for the answer start to end, you have to show the whole thing. Huh?
That's what you're trying to explain.
Yeah, that's what you said.
Yes. Well, so guys, stay with me, please. Location is 3. Wall is 3. Location is also 3. So basically, what's happening is we are looking at
I'm saying no.
one element. I mean, just to show wall. Oh no, I think I misspoke. We'll start here. And the action now starts, right? When wall becomes 4, location is 6. So we swap those 2. So finally we get some action. And wall is 5, location is 6.
I think our yellow pyramid needs to be bumped up. Round 1 should have 0 highlighted. Shouldn't it?
Mm-hmm. And now location is, wall is. So when you hit the last element, that means the array is sorted. So there you have it. The selection sort algorithm. Now somebody asked me, where is the code for this? How do we code this? So I provided a starting point here for writing functions and sub-functions yourself, right? And in the textbook, meaning on the website, I give you a chapter number reference which has the code. So if you look at selection sort, it's in chapter 7. And if you look at for bubble sort and insertion, it's chapter 23. So the code is there, but my suggestion is don't go there, look at the code. Time permitting, try it out. Try writing it yourself. So you can practice working with functions, loops, and decision-making constructs. It's a really good opportunity. Okay? So with bubble sort, the way things work, so assume entire array is unsorted. Starting from the end of the array, compare neighboring elements. Sorry, wrong spelling. Compare neighboring elements. If elements are out of order, meaning consider ascending or descending, then swap them. Right? Taking this action will bubble the smallest or largest element to the top. Increase the wall by 1. Wall represents what? Wall representing the sorted part of the array. Go to 2 and keep doing this, or we should say exit when you guys see that? Sort of? So that's the algorithm. So what I'll do is I'll solve one of the problems and I'll have you solve the other one. How's that? I'll take care of ascending, you take care of descending. Does that work for everybody? Alright, let's do it. So here is insertion sort. Oh no, bubble sort, excuse me. It's the last worksheet. Okay? So I'm going to do this in slow motion, the first step. So why is it hard to insert a row? Says insert copied cell. Okay. So I'll copy and find the cell. Okay, fine. So I want to show you how this will work. So I'm trying to sort the array in ascending order. I'm going to go through one round in slow motion. Compare neighboring elements. If they are out of order, swap them. Because my goal is to go in ascending order. Are those two items out of order? 98 and minus 344.
No, we're descending or ascending?
Ascending.
Which one?
Ascending.
Ascending. So,
Right there.
no.
It's fine, right?
Yeah.
So I'll just copy down 98. And again, I like things in the middle. So then I'll compare minus 344 and 56. Are they okay or are they out of order? We need to swap them, right? So I'll bring down 56 and minus 344. Minus 344 and 97, are they out of order?
Yeah.
Yes. So I'll swap them. I'll bring 97. here and minus 344 over here. Do you see minus 344 is bubbling up? That's why it's called bubble up. Or do you want to see it in color?
Is this all happening in one wall? Like,
Yeah, this is all one wall.
okay.
Right. Well, yeah, wall is always one. We just haven't incremented it yet.
Okay.
You probably mean it happens in the same loop.
Yeah.
Right.
Okay.
Minus 344 and 44. Swap. So we put 44 here and minus 344. What about the next one? Swap again. So we do minus 30 and minus 344. And again, right? I mean, so we'll say minus 20 and minus 344. So what happened was 344 bubbled up and heavier elements start to bubble down. But we don't talk about that. That just happens as a side effect. Yes?
Is this algorithm more efficient than the selection sort? Because even if it's going through in one wall, isn't the CPU still doing the same number of like comparisons? And
So which algorithm is more efficient, right? That is, it depends on the complexity of how the data is ordered.
right.
So it's hard to make a determination. So this is one round. So this is what this was the first round. Here wall was 0, right? And there is no point in looking at what? Location. Is location important here?
No.
Not really. So now wall is 1, and I have to do all that again. So this is the beginning of my sorted array. So great, I'll say in all the rounds I'll have that. So 98 and 56, are those out of order? So we'll say 98. What about 56 and 97?
Yeah.
Swap them?
Yeah.
So I'll say 97 and 56. What about 56 and 44? They're okay?
Yeah.
What about 44 and minus 30? It's okay?
Yeah.
And minus 30 and minus 20. So this becomes my second element that is sorted. Wall is now 2. Now the thing we can track, guys, is how many swaps are we doing?
Isn't 30 less than
Oh, minus 30 needs to bubble up. Okay, great. You guys are awake. I was just checking. Now, how many swaps did we do here?
40.
Well, it can't be 40.
What do we start with?
This is what we did, right? We swapped here,
10, 2, 3, 4, 5.
then we swapped here. I mean, we brought minus 344 all the way to the top.
4, 5, 6, 7, 7.
So we did 7 swaps. See, that helps you determine how the intensity of the algorithm, right? The intensity of the round. You're counting the number of swaps. What about the second one? How many swaps did we do here?
2, 3.
We did one here too, right?
Yeah.
So we did 3. So now wall is 2. How many swaps are we going to do? 0. So when number of swaps is 0, then I can say what?
That's it.
Array is sorted. So you see, bubble sort can be efficient in this way. Selection sort is expensive because you got to find the smallest element. Bubble sort you keep comparing and swapping. right? So you pay for it. You pay in computation time in all the different algorithms. I'll request you to please spend some few minutes and work on this one on your own or in pairs, however you see fit. All right, so here we have another array, and we are sorting this in descending order, high to low. So in the first round, how many swaps do we have?
2.
So compare from the right. I guess I'm going to have to go through this since I'm hearing variance in number of swaps. Let's figure it out. Starting from the right side, compare neighboring elements. If they are out of order, swap them. Are they?
Yes.
Because minus 14 is smaller than? We are trying to sort in descending order. Okay. Now, that was one swap. Wall is 0. Now we have minus 10 and minus 11. So that was the second swap. Minus 10 and 2. No swap. 2 and 4. 4 and 6. Sorry. 6 and 8. So how many swaps was that? 2. Alright, wall is, did the highest element bubble up? I know it was already there, but are elements, larger elements slowly bubbling up? Well, minus 10 did, right? So let's give that some color. Okay, wall is 1. How many max swaps are possible now? In a worst case situation, if I have 6 elements, then how many swaps are possible? 5. Okay. Minus 14 and 11. Need to swap? Minus 11 and minus 10. Minus 10 and 2. 2 and 4. 4 and 6. Are we done?
Yes.
All right. If I gave you this kind of a question in the test, you'll be doing it quickly. Now the entire array is sorted. So this can get complicated. How? Depending on the values that I provide. I could go, here things are already sorted in descending order. But depending on the order of elements, this algorithm could change. I mean, the complexity could change. Algorithm remains the same. Sorry. Question?
Why do you need round 2 already sorted in the first round? Why do you need round number 1 if we don't do any swap?
Now you're done. When swaps is 0, you exit. That's why I consider, but you have to go through that. You have to go through the loop and make sure that there aren't any swaps before you determine that the array is sorted.
So exit when swaps are equal to 0, right?
If swaps are equal to 0, then you exit. And you should double check the code in the book that is it optimized. The optimization that's required in bubble sort is when swaps are 0. Right? It's possible that they don't even, I'm not going to say that about the book, but if in an implementation they don't care about the number of swaps to be 0 and they keep it comparing and exchanging, we are wasting computing cycles, you see. So we have to get into the practice of writing optimal code. Please inspect the code in the book. So, very well. So, I guess this will make it in your notes as well. So you have the results. I should probably just post this Excel book. I'll do that. Otherwise, things in Notepad kind of get added. Insertion sort. This is like my favorite algorithm because it's the hardest to implement. It's the easiest to understand though. Because insertion sort is like what? You take a sort of, sorry? You were saying?
Oh, you insert something.
You insert something. It's like sorting a stack of paper. We all have done that, right? And you still have to work on ascending or descending. My dad used to give me this exercise all the time. Here is a stack of paper sort. It'll be a sort of like 400. And so what would I do? No. I would do it the old-fashioned way, the way the algorithm is. I'm just pretending that way because I need to explain the algorithm to you guys. So I have to stick to my story. I would take the first paper and put it and create a sorted stack. The first paper I would create, so I'll have two stacks. And I'll take the first paper, create a sorted stack. Then I'll take the second one and see if it belongs on the top or bottom of the first. If it belongs on the bottom, okay, goes there, we're done. Take the next one. And then I start comparing the elements or pages and find the position where the page goes, and then I'll insert it at that location. Right? That's an algorithm. That's insertion sort. We all have done that. Our dads always gave us stacks of paper to sort. Moms were more forgiving. They would just get us to do homework. Okay. So, insertion sort. Treat entire array. No. Actually, take first element in array and set, that means set wall equal to 1. Take first element array as a start to creating the sorted array. Does that make sense? I'll demonstrate with an example too, but does that statement make sense? I have an array and I'm basically saying wall is equal to 1, which means what? I have one element in the sorted array. Right? Then I'll take first element in unsorted part of the array and find the location for it in sorted array. Meaning to say, where does the first element from unsorted part of array belong in sorted part of array? So I have to find, does it go like in the first situation, in first case, I have to figure out, does it belong on top of the stack or bottom of the stack when I only have one element in the stack, right? So I have to take the first element in unsorted part of array and find the location and note the location where element should be inserted. That's the second step. Then I insert the element, make room for element to be inserted in given location, and then insert it. And number 4 is go to 2 until entire array is sorted.
Why did we take first element of array set to equal 1?
Well, when wall is set to 1, the index value 0 is the sorted part of the array. We need an example so it becomes clear, right? Okay, I understand that. So let me take you through an example, and then you can look at my description and see that story if it makes sense. So here it is. Array A2 is to be sorted using insertion sort in ascending order. So I'm going to say wall is 1. That means what? Negative 20 is the sorted part of the array. Oh, what happened? Sorry. So now I'll copy the rest of the array down, and what I'm going to do is I have to figure out if I need to figure out the location for minus 30, where it belongs. So I'll compare minus 30 with minus 20, and since I'm sorting in ascending order, does minus 30 belong before minus 20, or does it belong after? Before. Which means the location for minus 30 should be 0. So you see, it comes back to location and wall. Now location and wall now mean different things, right? So when wall is 1, that's to answer your question. When wall is 1, the 0th element is my sorted stack. And now I'm taking the first page or first paper from the sorted part of the stack, which is minus 30. And I'm comparing it with every element in the sorted stack. I only have one element there, minus 20. Minus 30 belongs in location 0. So now I'm going to make room for putting minus 30 in location 0. And obviously I cannot lose minus 20, right? So I'll have a temp variable. And I'll reduce the size a tad bit. So I'll put minus 30 in temp location, right? And I'm going to move minus 20 over. And then I'll copy the value from minus 30. I'll copy the value from temp to here. How did I do in explaining the first round? Did I confuse anybody? If you say, yes, you were very successful in confusing me. Then please let me know what questions I can help address. Are we okay, everyone? Yes.
How does negative 30 go to 0 from 10?
What? How does negative 30?
How does what's happening when the negative 30 is going to 0?
Okay, so this is where we were, right? So obviously minus 30 is in the memory, right? And what I'm trying to do is, I'm going to take the value that I need to move, the value that's in wall, right? I'm trying to put that into the temp location. So now this area can be overwritten, right? And so what I'll do is I'm simply moving that here, and then I'll bring minus 30 from temp to the 0th location, right? You need to see several iterations of this for the algorithm to be clear.
How is this different from doing a swap? Because don't you have to make an attempt to do a swap anyway?
Yeah, that's a very good question. So the question that she asked is like, why don't you just do a swap? See, because it's possible that the element that I have is like minus 344, and I may need to move many values before I can do the insert. So I'm just requesting a couple of minutes, allow me to go through a few iterations so you can see an example of that. So, yes?
So when you move negative 30 to 10, you're not moving the memory location, you're just copying the value inside the index?
Yeah.
Okay.
Right. Because when we say wall is 1, that was the assumption we started with, one element in the sorted part of the array. When we said location is 0, we are saying that the variable, the value minus 30 that is in location 1, because wall is 1, the real location for that is minus 30. And we need to put it there somehow. So we were trying to make room, and we were saying, okay, let's move minus 20 down. And we're not really going to disturb the rest of the array because that is the unsorted part of the array, right? So now wall becomes 2, which means, hey, I have 2 elements in my sorted part of the array. And I'm going to deal with this rest. And I'm going to take 44, which is the first element, and I'm going to figure out where does it belong in the sorted part of the array. Does it belong, is 44 less than minus 30? 44 less than minus 20? So it belongs where?
Where it is.
In location 2, right? So there is not much for us to do when location and wall are exactly the same. You can see that's the optimization that we can produce, right? So, all right, so I'll leave the values as is, and now our wall is 3, and location is also 3. See, location here cannot be greater than wall. Why? Because you're always trying to figure out the location only in the sorted part of the array. So location is also 3, as you said. So I'll copy all of this down and say wall is 4. And hopefully now life will be a little bit interesting, because so far it was very boring. All right. So now location is 4, that is my sorted array. Now I have 56, wall is 4. So now location will be 3. How do we determine this, right? So we need to, this is where we answer your question. We say, well, I need to determine the location for 56. How do I do that? I'm going to compare 57 with 96. I'm sorry, 56 with 97. Is 56 less than 97? No.
Yes.
Oh, it is, sorry. You guys are awake. Right? So I keep comparing as long as I am sorting in ascending order. I keep comparing 56 with every element going backwards until I come across an element that is less than 56. So 56 compared with 97, you said 97 is greater than 56, so keep comparing. 56 and 44. Okay. I've now come across an element in the sorted part of the array that is less than 56. Right? So location becomes 3. So you see, now what happens is I go to location 4 and I put that in temp variable. So I can override it. And then I can move 97 over and I can keep these guys where they are because they don't need to be moved. And then I can bring 56 over here. And the next example will be more friendly, or will show something more that you haven't seen yet. So now wall becomes blank. Wall becomes 5. So now I say minus 344. Compare minus 344 with every element in sorted part of the array until you come across an element in sorted part that is what? Less than minus 344. So we compare minus 3, 44, 97, no. 56, 44, minus 20, minus 30. So location is 0. Why is that happening? I'm sorry. I just
number 4 that is the same rows. Round 3 and round number 4. Do we need to swap 56 and 97 and put in round 4?
Yeah, that's what we did.
But it's, you did it in round 5.
Do I have an error here?
When you just put minus 2 in the temp, you change the same row around 1, right?
Yeah, because you're switching the position. And then, yeah, you just bump it.
You swap
Oh,
to the
right.
same row.
So this should have been minus 20 and minus 30. Now we're
Like that.
perfect. Thank you for pointing that out. So now, guys, this is a key example, right? When I look at wall and location and I look at the gap between the two, that's the number of moves I need to do, right? So I'm going to take minus 344 because that's the value we're going to put back into the array, right? So then I'm going to take 97 and I'm going to bring it to location 5. I'm going to take 56, bring it to location 4. Take 44, bring it to location 3. Minus 20, bring that to location 2. Minus 30, bring that to location 1. And then I'll take minus 344 and I'll put it here. Right? That's why you can't do a simple swap. Because you got to do all these moves. So insertion sort is easy to understand. Why? Because it's like sorting a stack of papers. But in the physical world, when you have a stack of papers, it's really easy. But when you have to do the instrumentation of this in code, when you write the code, that's where you have to really think about all these situations. So if you only have like few minutes to do code practice, I would recommend writing selection sort. Then bubble sort. And if you're still encouraged, to write insertion sort yourself. See, the code is in the text, it will always be there for you. But one of the things is if you try and do this implementation on your own, instead insertion sort is the most challenging of all the sorting algorithms. Not just the 3, but the full 8 set. And I still believe selection sort is the easiest. And insertion sort is just a lot of movement. I mean, you got to find the smallest element, then you got to move all these things. So, okay. So location now is, I mean, wall is now 6. Is the array sorted? Can you determine that just because you can look at it? Or do you have to still do something? You still have to do something. Because what if this was minus 980? You know, just to make life interesting. So 0 and all that again, right? But okay, no, I'm not in the mood. We'll just say location is also 6, and that's an example of optimization. Insertion sort. How are we doing on algorithm? I'd say we take a 5-minute break, and then we talk about 2D arrays. See you back here in a little bit. So 2-dimensional arrays are interesting because we add the concept of a dimension. And as mentioned last time, this is a way of organizing data. So if I have a 1-dimensional array of integers to track scores for lab 1, then I can do that. And if I want to track scores for lab 2, I could create another array called scores 2. And if I was getting paid by the number of lines of code I write, and if I had 6 labs to grade, I'll create 6 1-dimensional arrays, like we did in 36A. Just because we were not going to talk about 2-dimensional arrays. It was just to show you how painful life gets. It was. I remember grading as well. Sorry to put you through that, but now you can appreciate multidimensional arrays. So what we do is instead of creating a 1-dimensional array, we can create 2-dimensional. So I can say I have 40 labs or 40 students, and I have 6 labs that I want to grade. So you see, lab scores becomes like a table. Like so. So it doesn't matter which is x-axis or which is y-axis. I could say, just because it's convenient, I'll probably say I'm going to put all my, I'll say lab 1, 2, 3, and so on. But the thing is, I don't address these with those variable names. I address this as what? I address it with index value. So for students on this side, I can do the same. I will go all the way up to 39. So that will be how this memory is declared. Kind of like that table, if you can see. So if I now say lab scores 0, 0 is equal to 55, I write that Java expression, then the value 55 will go here. If I want to put something here, what will it be? That location. And this is like my favorite score, 100. If that was the maximum score, that is.
Does it matter if it says 3 and 11 or 11 by 3?
It depends how you declare the error. If you have, so let me do one small thing here. Sorry, obsessive compulsive behavior. Everything should be centered. Right? And how is this array declared? Like that, you see. So you should continue to address it that way. Because if you try and say 311, it's going to say, I don't recognize that. So that pretty much dictates. If you want to use, you can declare it as 640 and you'll be fine. Right? So obviously, guys, I can use a nested loop and what's the function you use for reading data? Which one? Scanner. Yeah, nobody's going to use scanf. There's no such Java function, right? Scanner. So you can use scanner in a loop and read all this data, or you can read it from a text file and bring it in, whatever. So once all this data is populated, the fun part of the two-dimensional array is that I can look at, so just for fun, let's say this student gets all these scores. And let's say on lab 1, I decided to give everyone this. It's because I can copy and paste quickly, that's all. So, that's not how I grade, by the way. I really look at every lab. Self-deprecating humor is the worst. Anyway, I can look at this as one dimension. So the point of a two-dimensional array is that I can look at the row and I can say student 0 and I can do some analysis. I can compute your grade. I can look at the average and so on, all using a loop, right? I can also look at this as a dimension and say, perhaps in a little different color, that the highest score for lab 1 was 55. The lowest score was 55 and the average was also 55. I can actually do that computation using a for loop, right? That's why 2D arrays are great. And when you add another dimension, you really need to understand what the concept of a dimension is, right? I mean, this is lab scores, but what if I wanted to use the same program and I add a third dimension and I say, you know what, I'm going to teach at Lianza for 30 years. I teach every quarter, so that's 120 quarters. So I'll add a third dimension. And I'll put 120 quarters. So I can go from quarter 0 to quarter 119 until I retire, and I can use the same one. And all that, what does that do to memory? What's the size of that array? 120 times 6 times 40 times 4. So you can keep adding dimensions. Maybe I teach in 3 colleges every quarter. So now I can add a 4th dimension, which is the colleges I teach in. Are you getting the rhythm? Well, programmers can do everything, right? Maybe 3 colleges on different planets. Yes. Question?
Would you put the 3 before the 40?
Oh, it doesn't matter.
Oh, okay.
As long as I know what dimension means what.
Oh, okay.
Now let's talk about your lab assignment. And fortunately you're only dealing with, oh, this would be a syntax error, by the way. You need 4 dimensions, right? Okay, so he said, let's not get too crazy. So I'll come back to Earth and I'll dream about multidimensional arrays later. So which means what? That let's look at your assignment. Assignment 1, lab 1, project 1, same thing. Now the way I'm writing the requirements for you guys is as if a marketing person has written those. Is that okay? Well, it's going to have to be because that's how it is right now. So this marketing person is saying let's have some fun with multidimensional arrays. They don't know what it is. They say consider the picture below. So this is one big picture, not 2. I've got Apple revenue by location. And I've got iPhone sales by location. Well, by region. And this has 6 regions: America, Europe, China, Japan, rest of Asia, and retail. This has APAC, Japan, Europe, and America. America is in both. Europe is in both. Japan is in both. And APAC is here. And APAC is not in, it's separated out. China, Greater China, rest of Asia, and retail. Right, because APAC, I think it stands for Asian Pacific something. So this is the output I want. So you can, for this purpose, say China and rest of Asia is APAC. Okay? And I want some output that looks like this. And you're required to use multi-dimensional arrays. I think if you create 1 dimension for geography, maybe you can track APAC separately. Maybe you can just add 1 more line, and I have a typo here. It should have said retail.
What about retail drive?
It was not there. So that's what I'm suggesting, that as you consider the declaration of the multidimensional array, you can create 1 dimension which tracks all the locations. And instead of having 6, you can have a 7th one, which is APAC. And you can list APAC separately, right? And then you can have 1 dimension that tracks Apple money and iPhone sales together. So like Apple money can be index location 0, iPhone sales can be 1. And then you can just print out the result. You have to print total Apple revenue and iPhone sales by region. And the totals are already shown here, guys. So it's a matter of what? This problem is more about looking at the requirements and your ability to come up with a proper array declaration. That's all. You can do this problem probably in 30 to 40 lines or less. Okay?
Do you want us to user input or hard code?
I don't care. I mean, you have used scanner enough, right, in 36A. If you want to show it off again, go ahead. It doesn't matter. Does everyone, you all have used scanner, right? But you can hard code, or if you want to get fancy, create a text file, so we can give the program to Apple guys and they can change the text file and, you know. Have a great evening, everyone. I'll see you on
Monday.